name is Tommy, and today we're looking at resonance and formal charge. So, when we draw the Lewis dot structure of O3, at the end it's going to be a little different because we'll see that we have two different bonds. But I'll draw it out and we'll see. So O, 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 connect all with a thing. 3 times 6 is 18 valence electrons that we need to worry about. We have 2 bonds, single bonds right now. So we subtract 4, we get 14. And if we go all around right now, we'll be 2 electrons short. So we need to do 2 for 1, or 2 pairs of electrons for 1, a double bond, 3 pairs for the other, and 1 for the center. And that should be 2, so that's 12, 6, 6. So that gives us our Lewis dot structure of ozone. But this predicts that one bond is going to be longer than another, which in this case is not true. Experimentally, we find that all bonds are the same length. So to make up for that, the Lewis dot structures will use resonance, or it'll be little arrows pointing and showing that the structure could also look like this with the double bond over here. And the way we signify it is by putting all possible structures with an arrow, with a double arrow between them. So as you can see, all we did was just make another one with a double bond somewhere else. And you do that as many times as necessary. But for ozone, we only have to make 2. For this problem, all of these are valid Lewis dot structures of fulminic acid, but only one of them will be the dominant structure. So the way that we look for that is through formal charges. And the way we do formal charge is that we figure out how many valence electrons each atom in a compound has. So hydrogen gives 1, carbon has 4, nitrogen has 5, oxygen has 6. And then you count the amounts of bonds and electrons. Each electron counts as 1, and each bond counts as 1 for an atom's formal charge. So for hydrogen, it has 1 bond, so we subtract 1. For carbon, it has 2 bonds and 4 electrons, so we subtract 6. For nitrogen, it has 4 bonds, so we subtract 4. For oxygen, it has 3 bonds and 2 electrons, so we subtract 5. And that gives us 0 for hydrogen, -2 for carbon, and +1 for nitrogen, and +1 for oxygen. So then we keep on doing this for every single one. So again, hydrogen has 1 bond, so we subtract 1, it's 0. Carbon has 4 bonds, we subtract 4, it has a formal charge of 0. Nitrogen has 5, has 4 bonds, we subtract 4, it has a charge of +1. Oxygen has has 6 electrons and 1 bond, so we subtract 7 from 6 and we get -1. Cool. For the bottom one, again, hydrogen has 1 and we subtract 1 for the bond. Carbon has 1, 2, 3, 4, 5. So we have 4 and we subtract 5 and we get -1. Nitrogen is 5 and we subtract 4 for the 4 bonds and we get 1 +1. And oxygen has 6 and it has 4 electrons, 2 bonds, so we subtract 6, and we get 0. So none of these completely minimize formal charge, but there is one thing that if they don't completely minimize, you can look for. You want to look for the one that has the negative formal charge on the most electronegative element. So of H, C, N, and O, the most electronegative is oxygen. So we're looking for the one that has a negative on oxygen. So A has a +1, so it can't be A. C is 0, but B has a -1. So B would be the dominant structure of fulminic acid.